Hello everyone, my name is Yang Chen. I'm from University of Tsukuba. Today I'm glad to present our work, Virtual and Mark-based control of docking support for assistive mobility devices. So first, let me introduce the background. There are a lot of wheelchair users around the world. Powered wheelchairs operation requires docking as daily activity. So two typical scenarios are shown here. On the left side, a standing wheelchair is needed to dock to the front of a chair. And on the right side, a normal wheelchair needs to dock to the side of a driver's seat in order for the user to transfer into the car. Controlling the docking maneuver to a conventional chair or bed is usually difficult for individuals with lower limb disabilities. Therefore, we consider that it is possible to automate this process for assisting. So first, we defined a generalized virtual landmark as shown in red arrows here. The virtual landmark is inferred from the object, and it is also the place where the wheelchair needs to arrive. For generating the virtual landmark, a camera is the most common and viable choice. Therefore, the field of view constraint comes. So how to keep a real object inside the camera's field of view while docking to a virtual landmark inferred from the same object is a problem. We can rephrase the problem by mathematical symbols. By setting two polar coordinate systems on the object and the virtual landmark individually, we can get the virtual landmark as r beta lambda. For simplicity, we align the center line of the camera with the center line of the wheelchair. Then the pose of the camera becomes 0 L half pi. So the problem becomes a wheelchair with a camera fixed at 0 L half pi docks to the pose r beta lambda while keeping the alpha star within the field of view defined by alpha bar along the trajectory. Alpha bar is the angle from the center line of the wheelchair to the connecting line between the camera and the objective. So here are some related works, such as about wheelchair docking. For example, the autonomous docking of a wheelchair to the car, or a docking control method in narrow space, or a shared control strategy for docking and obstacle avoidance. However, the challenges from the field of view constraint have not been handled, even they all use visual sensors. Due to the similar kinematics, we also reviewed the works about mobile robot docking. The first work, they proposed a spiral curve as planned path. However, they could only control the position, which means the beta of the virtual landmark is ignored. In the middle, they propose a controller to realize a successful docking. However, the objective and the virtual landmark are considered as the same point, which means alpha equals 0. The third work, they propose a dual-mode predictive controller, which is more computational expensive. Also, the virtual landmark is simplified to beta equals 0. So the general virtual landmark is not completely considered in these works. So the purpose of this work is to develop an autonomous docking support system for assistive mobility devices. The docking behavior is actually one pose aligns with another pose. For getting the another pose, we need pose estimation. For this alignment, we need motion control. For the motion control, two constraints should be considered. One is nonholonomic motion constraint, and another one is the field of view constraint. For the virtual landmark estimation, we use a depth camera as the information source. We only use the depth information without any additional landmark. For the recognition of the chair, we will rely on the user's intention. We assume that the user has aligned the wheelchair within a close distance with the chair. Then we use some simple filters and a cluster extraction method to get the chair, and separate the chair into back and bottom surface by height, and calculate the centroid of back and bottom. Then project the centroid to a horizontal plane. For getting the virtual landmark, we connect the centroid and derive the virtual landmark when lambda equals 0 first. Then we generalize virtual landmark for any given lambda by rotating the connect line around the objective. For the motion control part, we aim to design a nonlinear feedback controller. The pulse alignment can be expressed as rho alpha phi converges to 0. Rho is the distance between the center of the wheelchair to the virtual landmark. Alpha is the angle from the connecting line between connect line to the center line of the wheelchair. Phi is the angle from the posture of the virtual landmark to the connecting line. So here is the controller we designed. The blue part works for rho alpha phi converge to 0. The green part is responsible for constraint alpha star. Alpha star is actually a complex formula. The asymptotic stability of this controller can be proved by Lyapunov indirect method, which also help optimize the gains of the controller K1, K2, K3 as shown here. So by now we have proved asymptotic stability. However, the global stability has not been proved. Instead, we pursue a feasible space where the local stability could be guaranteed. We did a simulation for different cases. The arrow here represents different initial states of the robot. Then we select the feasible initial states by convergence and no violation of field of view. Here, the black arrows are those meet the requirements. The red arrows are those do not. We can check the trajectories from those selected initial states, as shown here. They could all converge to the virtual landmark. Then we can also confirm the alpha star is kept within alpha bar all the time. For making our solution more general, we try to fit the boundary of the selected initial states by inequalities, as shown in the middle. For verify this fitted boundary, we selected some sampled initial states inside this space. And we redid the simulation and found out that the trajectory from those sampled initial states could also converge to the virtual landmark. So finally, we can see the convergence and the violation of field of view are both guaranteed in this regulated control law. Then we did an experiment to verify the proposed autonomous docking support system. The robot platform we used is Colo, a standing wheelchair. We randomly select the inertial states inside the feasible space. We also define a safety region around the virtual landmark, which means that only if the wheelchair enters this safety region, the user will be able to do any final alignment. The evaluation includes virtual landmark estimation, convergence, and then the violation of field of view. So here are two example videos. On the left side, on the corner is the virtual landmark estimation. This part is the chair's back, and the pink points are chair's bottom. The blue cube is the center of the chair. The red arrow is the virtual landmark. The coordinate is the center of the robot. So we can after that we can confirm the rho alpha phi convergence. As we can see, they all decreased to a small value, which is exactly within the safety region we defined before. Also, we can confirm the alpha star is kept within alpha bar all the time. Then we did more tests, as shown here. We can see the trajectories all converge to the virtual landmark. Also, the row alpha phi were kept within the safety region. The maximum alpha star along the trajectory always remained within the alpha bar. So here is the conclusion. We defined the docking problem by a complete framework that generalizes both the virtual landmark and the camera parameter. We proposed and verified a solution which contains a virtual landmark estimation method and a nonlinear feedback controller. The local stability and no violation of field of view are both guaranteed inside a fitted feasible space. The proposed docking method could be potentially applied to any assistive mobility device and kinematically constrained mobile robot. Our future work includes exploring the proposed approach with user riding for evaluating the effectiveness and the perception of the user to verify what needs could be met. Thank you. I welcome your questions.